physics examiners love questions like this. They love bringing things from different modules together, even a bit of year 11 electrostatics, and applying it in a new way. The knowledge that you're applying here is the photoelectric effect. Okay, so first of all, let's have a look at this electroscope. This is a gold leaf one. You might have the one with the needles like that. It's the same principle. If we remove or add electrons to it, remember it's a sea of delocalized electrons, all trying to get as far away from each other as possible, so they'll spread themselves out, which means that you're going to have some negative charges on those two parts that can move, and the electrostatic force is going to push them apart. Now, in the lab, we often experience electrostatic forces as quite weak. It seems a whole lot weaker than gravity, really, but that's because we're dealing with such tiny differences in the amount of positive and negative charges. In reality, the electrostatic force is surprisingly strong. It is much, much stronger than gravity. It's what makes solid things feel solid, right? So atoms are mostly empty space. What stops that hammer going through that piece of steel is those clouds of electrons on the outside of the atoms repelling each other with the electrostatic force. So think about it. You throw something off a building. It takes all of the 10 stories for that thing to accelerate up under gravity, but under the electrostatic force, it can stop in a couple of millimeters when it hits the concrete. So let's have a look at this piece of zinc down at the atomic level. So those red pluses, they're the protons of the center of the atoms, and they're locked together in this metallic lattice. And the electrons, well, they're all, for every proton there's an electron when it's neutrally charged, but they're all moving around. The nuclei are vibrating and the electrons are moving around as this sea of delocalized electrons because of the thermal energy that the material contains. So I'm going to take that away to make the next lot of explanations kind of seem simpler. But remember that that's kind of always what's going on. So let's now make the plate negatively charged. And to do that, we're going to add some extra electrons to it. Okay. So now we've got these extra electrons, and you can see now there's an electric field pointing towards the plate it's negatively charged. That's the force on a positive charge. Remember, it's the opposite direction for force on a negative charge. And we're going to hit it, we're going to do the question the other way around. We're going to hit it with a photon, a red photon. So a photon that hasn't got that much energy. It's got less energy than the work function. So it transfers extra energy to that electron, but it's not enough energy now in total for it to break free of the surface of that metal, and so it just returns. Change the situation around. We're going to use a violet photon of light, a photon with more energy, and let's assume that it's got enough energy now to overcome the work function. So that electron's now going to find itself outside the surface of the metal. But remember, it's an electric field that's got a force on it away from the plate. So even if it just breaks free with a little bit of velocity, once it finds us outside the plate, then the electrostatic force is going to accelerate it away, and it's not going to return to the plate. So the plate's going to become less negative than it was before. Of course, what will happen though is that an electron from somewhere else in the electroscope will now get attracted, because that part of the electroscope is slightly not as negative as the other part, and so another electron from somewhere else down below is going to move up there, and that's why we see the needle at the bottom start to show less charge, because overall the electroscope's got less charge. It's worth saying, though, that just because a photon of light might have enough energy that exceeds the work function, it may hit an electron that's kind of deeper in. And so that work function is actually the minimum amount of energy it takes to break an electron free. It's what will knock out the lowest hanging fruit of the electrons at the surface. Okay, so now let's make the plate positively charged, and we do that by taking away electrons. You can see that the electric field has now changed, so there's a force away on positive charges, and we're going to hit it again with a violet photon of light, which, let's say it's got enough energy and it hits one of those low-hanging fruit and they find itself away from the plate, except now it's in this region of electric field, so it might have had initial kinetic energy like this, but it's going to be like a projectile. There's a force that's going to force it back onto the plate, and so the net charge on the plate in this instance won't change. Of course, all this is lovely theory and animations. What actually happens in reality, I'll let some amazing guy from the Institute of Physics show you in reality what happens in this situation.